remind you how tough it is to be a woman in neurosurgery. But actually, in this giant world, there is one picture that stands up, and that's the picture of Elizabeth, that she has an incredible path. She actually graduated as an engineer at Duke with a double major in biomedical and electrical engineering. And then she did an MD, Ph.D, specializing in pediatric neurosurgery, as she mentioned it earlier this morning. And she completed a residence at Pitt, which is actually the highest volume program in neurosurgery in the entire United States. And so she has an incredible background, both in engineering and in neurosurgery, which actually led her to be the first person implanting a human brain array into the sensory cortex in the world. She has a very high skill in intracortical BCI program, and she actually being a very long friend of our RNEL lab at Pitt University. Right now, she actually moved to Austin, where I'm sure she will do a great job, and she will actually be a real model as a woman in neurosurgery. So thanks, Elizabeth, and stage is yours.
Why, thank you very much. That was a very generous introduction. So I'm going to try to share my screen, and hopefully this will work. So let me know. Do you see a slide up there now?
Not yet.
Not yet. Well, let's give it a minute and see if it shows. Occasionally, we have to change our mind. Let's try. All right, let's see if it'll show. I think we'll do that one.
Yes.
All right. Is that showing now?
Yes, it is.
Okay, wonderful. I'm just going to make this a little bit bigger for me. All right. So I really would love and hope for this to be somewhat on the interactive side, which is always a challenge when we're trying to do this virtually, because I'm not sitting in a room where I can see people always sticking their hands up. So I will try not to speak for too long so that we can really get to a point where we can do some interactive stuff at the end. But I wanted to take sort of a slightly different approach. You all have heard tons of, very detailed and expert discussions about all sorts of research that people have been doing. And I'm going to take a little bit of a different tact. Because what I really want to stop for a moment about is actually think about what goes into designing the devices that we would be using for brain-machine interfaces on a clinical side. And so to sort of jump into this, let's see if we can get our pages to advance. I'm sure that I can make my pages advance, although occasionally I've had trouble with this. There we go. We did make it work. It woke up. So there are a couple of IDEs that are included in the work that I'm going to show. But just from a clinical standpoint, I think of this as sort of the world of restorative neurosurgery, but it actually spans far more fields than just neurosurgery. And so, if we look at the things that have been done to help restore hearing, cochlear implants have been developed and are widely used. And one of the things I care about is that it turns out that they are extremely beneficial when implanted in young children very early on, because they adapt very well to learning to use them. When I started as an undergraduate in biomedical engineering, my goal was to be involved in developing a retinal implant that directly plugged into the occipital cortex. And actually, while I was an undergraduate, the Utah array was developed. And I said, oh, this has all been solved. We're going to have restored vision by the time I get out of medical school. And look where we are today. We still have a lot to do. And that really, the world of neuroprosthetics just continues to grow. If we look at the patients who have lost the ability to communicate, and I think the group that I'm most familiar with are the locked-in patients, so brainstem strokes or other injuries that have damaged their ability to communicate because they're actually not allowed to, not able to form words, but their mind is preserved. And so people have been looking at EEG as well as cortical implants as a way to be able to restore communication, because for so many people, that seems like that's the really most important thing. Restoration of movement, whether it is in patients that are quadriplegic or have paralysis or loss of limbs, has been a big thing. Our group in Pittsburgh was very interested in looking at the ability to add sensory feedback back into that model. And then the groups such as Eddie Chang and Liberty Hamilton have really been looking at the ability not just to restore communication, but really specifically to be able to look at ways of restoring speech. And so the spectrum of neuroprosthetics that we are looking at is actually very, very broad. But I think one of the other things that is really important is to look at the end user or the patient. And so I mentioned the locked-in patients. ALS patients often sort of fall into this category also. This is a group of patients that traditionally had eye gaze, and that was really the only means they had for communicating, whether it was blinking for yes and no, or potentially Morse code. But also these patients have very limited lifespans. And so they have been a patient population that many people had advocated were ideal from the standpoint of, if you will, the research of being able to do restoration of function. Quadriplegic patients then sort of probably fall into that next group because they have such a decreased ability to interact and sort of but I'm not sure it's fair to say that they have a decreased quality of life, because there are definitely quadriplegic patients that live very rich and full lives. But again, they become a group that is pretty easy to look at as being an end population. One of the ones where we have had more trouble with is working with patients with just partial paralysis. So we've done some short-term studies where we've worked with people who either had a brachial plexus injury, so they had a single arm that was not functioning. We have worked with a sort of a unique ALS patient who had loss of function of his arms, but not his legs. But when we sort of have approached particularly the FDA about looking at working in stroke patients for long-term implants, they have really, we have had a lot of pushback about why would we want to work with somebody who only had partial disability. And I think that some of that fear is there risk that we would cause them more harm? But also I think there's a sense that in some people that, okay, just because they have one arm that doesn't work, they don't need some sort of invasive neurotechnology. And so the question is, where do we move that needle? When we talk about amputees, I think we see lots of people who are interested in prosthetics that have muscle control, so that you actually have not just a passive prosthetic, but something that is active. There's been a fair amount of work with that, both in lower extremities and in upper extremities. One of the interesting things in the lower extremities is a lot of work in thinking about self-balancing prosthetics. But again, all of those are without sensory feedback. And then the last one that I can't not include is, as we develop all these devices and these technologies, what about the able-bodied person? What about the military wanting to use these devices to augment function? And just for the record, in 2003, I wrote a white paper for DOD about doing a burr hole, so just a small hole, and using a self-deploying electrode array, which would be able to augment function. So this is something that has been at the interest of the military for a long time. what about athletes? What about people who have the money to buy technology and wish to be able to augment some part of their function? Are we going in that direction, or are we somewhere going to draw a line of what is acceptable and what is not acceptable? And I think those are all things that we have to pay attention to as we are thinking about where we're going to go. Sometimes it's really easy to be hanging out in the lab and not think about what the implications are. But certainly it's something that becomes an important piece. And then I would say the next thing is really what is our goal? And we've talked a little bit about this, and I addressed that a little bit of, okay, are we talking about restoring function to the ability to be able to open a refrigerator versus being able to recapitulate being a concert pianist? Or are we really just talking about assistive technologies where we're controlling smart wheelchairs, or we're have a system which is controlling a keyboard, or is it just being able to turn the lights on and off in the house or answer the phone? And then when we move beyond that, and I think that John brought this up a little bit, of that window where we have that plasticity after an acute injury, are these technologies that we can really use to augment our rehabilitation? Is there a way that we can push that window of where we have that opportunity to relearn? And then, as I said, just as I touched on, are we talking about the ability to augment for able-bodied people? And so if you have a patient who has, let's say, one of the variations of autism, and we can do something to improve their social interaction, is that an acceptable use? And again, those sort of become some of the questions that we need to keep in the backs of our minds as we move forward. Now, we always talk about the available technology. And we've always started with the non-invasive components. Some of these have pros and cons, and we can talk about them. But certainly from a risk to your patients, EEG certainly has little to no risk to your patients. Doing things like MEG, or magnetoencephalogram, or functional MRI, where we're using that as a feedback mechanism to augment rehabilitation. Maybe that's a very reasonable technology. Many people, when I first sort of entered this world, talked about being able to put in non-penetrating electrodes. So whether we were placing those on the surface of the brain, or on the, actually putting them outside the brain, so between the skull and the dura, and then actually more recently I've had conversations about putting them beneath the galea, which is the thick fibrous layer under the scalp, so between that and on the bone, or potentially putting them under the temporalis muscles. Many people seem to have a notion that those technologies are less invasive, and therefore maybe those are the things that we want to consider. When we compare them to the invasive technologies, so these are things that would actually penetrate through the surface of the brain. The richness of the amount of data that we can collect is different. But again, I think you really have to frame your decisions about which technology you want to use based on how much data do you need in order to provide the assistance or the technology that that patient needs. It's very interesting. A lot of people, when people talk about penetrating electrodes, one of the big things that people originally said to me was, well, why would you put this in? You're going to damage the brain when you take it out. You're going to eliminate the ability to ever do something there. And so we know that that's not accurate. We have taken electrodes out of people's brains And it's kind of cool to see because you do have a scar area there, but they come out pretty easily without a lot of damage. We have moved electrodes in people's brains, and we've been able to do that successfully and not generated new deficits. Now, some of the electrode types that would literally integrate with the brain, perhaps those have some different concerns, but many people have felt like if we could use electrodes that actually integrate into the brain, that perhaps we eliminate concerns of scar tissue forming around the electrodes and therefore degrading the signals or degrading our ability to stimulate the brain. But we certainly add a level of complexity if we ever want to be able to remove those electrodes if they're actually integrated into the brain. All right, so I'm going to use a couple of videos of things that have been done. And what we're going to, and the reason for doing this is to kind of give you an idea of where we are. So we can see that one option here is with pedestals sticking out of the head. But this is free-form control with 10 degrees of motion. The only feedback she has for performing this is actually her visual input of where the hand is. And yes, you know, these kinds of things are done with somebody standing next to the stop button, so you can't harm somebody. But one of the things that we know is that for that kind of control, if we take away her vision, she no longer has any control over that robotic arm. And for all of us, if we close our eyes, we're still able to reach out and touch our nose. We're still able to achieve other tasks. Now, that's not to say that that's just a great party trick, because we are able to actually establish the kind of control where potentially this could be an assistive technology. And so, you know, we can get to a point where an individual can interact with the robotic arm in such a way that they could, in theory, improve their quality of life. But even in this, you can see that there's some limitations to that ability, because although she can grasp a variety of different things, the robotic arm is not attached to her. So yes, it could be attached to a chair to go with her from place to place, but there's certainly still some significant limitations. So one of the things that we did in Pittsburgh, because we really thought that adding the cortical stimulation piece to this was so important. Let's see. So by putting electrodes into sensory cortex and then mapping what areas of sensory cortex they represented, and then using a robotic arm that has sensors when it is moved, and I doubt that you can hear him answering which finger's being pushed, but by providing stimulation directly to those areas that we had already mapped out that corresponded to the 4 fingers, we're able to provide him with some sensory feedback. And we are able to sort of do something like, which I will call gross 2-point discrimination. It's certainly not fine 2-point discrimination. But again, one of the big questions that being able to add sensory feedback adds to the questions, well, is this relevant? Does it actually make any difference in what we're doing? And so that's actually kind of a challenge to answer. And part of it is because the testing that you can do with somebody when they are using a robotic arm is fairly limited. So what we have done is to use some standard occupational therapy tasks. And so what we see is when we add the sensory feedback, and so essentially what that's doing is it's not proprioception. So don't get that wrong. But what it is essentially as the hand comes in contact with the object, that provides stimulation back. And so now you have a component of this that is not entirely just judging where the hand is in space or entirely by visual feedback. And so what we did see was that it improved the fluidity of the actions and it improved the time to doing them. So there probably is some value in being able to look at being able to do integrated motor control with sensory feedback for what we offer to our patients, if what we're really trying to provide is this kind of very, well, I don't know, maybe I should call it gross motor activity, but things that would be activities of daily living. So with in mind what some of the things that we can achieve, let's go back again to the technologies that we have and what are our limitations and how do we do that. So the patients, most of the patients I've worked with are quadriplegic. So if we're working with an EEG cap that's going to be able to provide us with some degree of control, how do we get it on? So somebody who can't use their arms can't put their own cap on. So therefore now we know we have to have an aid present. Now, if what we're really doing is using this in the rehabilitative time frame, then maybe this is a great technology to look at. I don't think that anybody is ever going to argue that we are potentially putting our patients at risk of injury if we're working with those kinds of technologies. Now, the one problem though is, especially if we're looking at fMRI or magnetoencephalogram, these things are giant and they aren't actually readily available. And if you have a patient who is quadriplegic, they have to transfer in and out, and you do actually now incur some risk associated with falls and those kinds of potential injuries. And while those are theoretical, I will tell you that in the years that we've been doing this, we've had a patient that's has fallen while getting into the MEG. I have patients that have fallen getting on and off of an fMRI table, on an MRI table to participate in a study. So these things are real. But they certainly provide some options, although probably not very, well, if we're doing feedback things, then maybe they're useful. So what if we then move to putting things into the subdural space? And I think that, you know, if what we're trying to do is relatively simple types of tasks, placing electrodes in the subdural space or the epidural space is probably very realistic. One of the things, and you'll notice if we look at this one, we have a very long tail on this electrode. And so to help solve sort of the issue of having plugs sticking out of the head, what we did is ran a very long tail and then tunneled it out onto the chest wall, much like you would do with a central line. And so now your care is much like a central line. And we know that from dialysis patients or other patients that need lines long-term, you know, this is a viable solution for years if necessary. And it opens up all sorts of other options sort of from a like pacemaker standpoint of, you know, can you put a can on the chest? The chest is very accommodating. Now this provides you with a way of getting your data in and out and potentially makes it fully implanted. But the richness of the data you're going to get is simply by the nature of the fact that you're using a smaller electrode array is going to be limited. But certainly for being able to interact with household devices, for being able to interact with a keyboard, this might be more than sufficient. If what you're trying to do is to boil water and pour a cup of tea, we might decide that this is not. The argument that this is less invasive, I'm not sure that I buy that. I'm going to let you all make some of that decision. This still requires a surgery. It still requires an implant. Therefore, it still has a risk of infection and a potential need to remove a useful device even if it gets infected. All right. And then, so then as we move sort of through our list of technologies, then we move into our more invasive technologies. And so many people have argued that we want to be able to collect lots of data. One, I don't know, I think most engineers like lots of data. I think I'm beginning to believe that most neuroscientists like lots of data. For the people who grew up doing understanding cortical control from looking at single units or local field potentials, everybody is very comfortable with the invasive technology. But it is invasive, there's no question about it. And it would not be a neurosurgeon's talk without at least some operative photos. So one of the things I'm going to point out in this particular slide is that this is not normal cortex, despite the fact that this patient was billed as having no central abnormality and was thought to have something that was really a peripheral abnormality. We now know from family history that this patient has some unique form of MS because she now has many family members. But in fact, what you're looking at here is a slightly atrophied brain with a very thick arachnoid. So no neurosurgeon in their right mind, I don't think, would try to put an electrode through that. And so we dissected off all of that thickened arachnoid. And so here are two arrays that are implanted. And one of the pieces of that really had to go into this planning was that in our original plan, where we wanted an electrode was right here, all right? But this is a big vein running across the surface of the cortex. And so we couldn't put an electrode array there. And this was actually lots of fun because the surgical planning was done by a neurosurgeon and some other physicians who are not neurosurgeons and a bunch of engineering students. And so really there was this big debate about whether or not we needed to have multiple surgical plans. And I insisted because I was pretty sure the place everybody wanted me to put the electrode was where there was going to be a vessel. So we went with plan B so that we could get around the issue of the vessel. And so now you can see these plugs that we have left here, and we've got them covered up. And then this is what we get the bone put back in. And I will tell you, because I took her electrodes out several years after they went in, all of this bone had completely healed, which is what we expect. That's, as neurosurgeons, that's what our expectation is. We had hoped we would be able to recover this in its entirety, pedestal, wire, and electrodes. And we were not, because the wires were really totally intercalated into the bone. So we ended up having to collect them just as separate pieces. And then here we are with our pedestal sticking out of our head. So, you know, one of the challenges that this presented is that we have to worry about infection. We have to worry about how the scalp reacts around this. And this is very close to the device. So if there is an infection, you have a much higher concern that you may actually lose your implant. There are other problems with doing these kinds of implants, and that is that all the chairmen in your department and your collaborating departments all want to be in the operating room with you. And so you have to figure out ways to limit who gets to go to the operating room.
Elizabeth, you have 2 minutes more.
Okay, no, I am wrapping up, I promise. So again, the thing that we want to look at is, what does the end user need? What do the patients need? So ease of use needs to be one of those. Reliability needs to be one of those. And then adaptability as our patients change and their needs change. And last, they need to be able to accept the devices that we're doing. So one is we really need to move to a fully implanted device. From a reliability and stability, we know that we can record neurons out for 3 years, but we also need to look at ways of how do we generate stable decoders so that they do not have to have a technician who's updating them constantly. And then we talked about blended devices, and so this is an example of a robot that uses vision to pick up an object and deliver it. And what we found is in order to have acceptance from the patient standpoint, they needed to be able to have control. And if they didn't have control, then they were unwilling to or unhappy about interacting with that device. And finally, for what indications do we put these in? When do we do it, early or late? Who gets them and who picks up the cost? We've collaborated with many people over the years, many funding institutions and sites and industry, but none of this could happen without the volunteers who participate. And at that, I open this up to discussion.
Thank you, Elizabeth. Wonderful talk. I think it really gave a very nice perspective of BCI field. It was wonderful. So we now have a student, Marco.
Anthony Shruti.
Yeah. Hi, Elizabeth. So being a biomedical engineer, I think you're truly an inspiration for us. And right now, we don't have any questions from the students, but I pass on mic to Marco because he has a question.
Yeah, I actually, I mean, as many of us listening, I think I have many questions, but I would choose one, and actually is specifically because I work with lower limb, and so when you look at what has been done in BCI, recording from motor cortex in patients, of course, we are not looking at the lower limb because, well, if it's a paraplegia, there is so much that you can still do with your arms. So, and touching the brain is a little bit touchy. If it's a tetraplegia, the first thing you want to recover is the use of your arms. But I was wondering, apart from like a lesser need maybe to directly tap into the cortex in this case, from a surgical perspective, is it actually particularly complex in the sense like if you were to look at the representation of the leg in the sulcus, do you think it's something feasible or not, looking at the representation of the leg?
So I think there's a couple of ways to think about that. If you thought that recordings, not micro recordings, but something that was more of a subdural grid, for years we have slipped electrode arrays into the inner hemispheric fissure when we were doing epilepsy. So we know that that's feasible to do. So depending on the sort of the amount of data you need, that's certainly a possibility. Now you would have to open the dura to get there, because it really is, if to come from here, you have to come through the sagittal sinus, and that's not going to be an option. The other thing that people have talked about is if we sort of move past the idea of penetrating electrodes, you could use long shank electrodes and really come in from the top and be able to reach the areas of interest. I think maybe the area that is even more interesting is that a number of groups have been looking at the idea of essentially electrodes that would kind of unfold themselves once they were in the spinal fluid space and allow themselves to drape over the surface of the brain. And so potentially something like that, especially if it is navigable, would provide you with an opportunity to access that part. I do think that for ambulation, it's important not to ignore the possibilities of the information that we can get from the spinal cord. Particularly if what we're looking at is just simple restoration of locomotion, and not necessarily dancing. because I think there is some possibility that we could achieve signals that would provide us with enough to sort of be able to trigger a locomotor circuitry to allow us to restore some gait.
All right. I think we have few questions from the attendees. So I guess I read out one. How do you see implementation of chronic implantation in the brain occurring in the future? For example, Stentrode, among others, are beginning to show signs of higher channel count, non-invasive implantation for chronic use.
So I think the question is about what are the options for chronic implants?
Exactly, yeah.
So I think that's something that's going to actually be very interesting to see what comes along as we move forward. I have spent time talking to a group that was very interested in really using optics and infrared as a way of looking at data from the brain as opposed to putting in electrodes. Mm-hmm. We certainly have ionophores and things that can look at the transmission of actual molecules. And so maybe some of those things will provide us with information. Again, it always becomes a little bit of what data, what kinds of data do you want in order to translate them into an end product. And so, if what we decide is what we really need to be able to do is to do 1 year implants to really help in the acute rehab phase, that's likely to look very different than somebody who is a well-established quadriplegic who needs an assistive device that allows them to plug and play with their home.
Yeah, that's a great answer. And
sorry, Anthony, I also actually have a question. I was wondering, how do you see instead BCI, because now you showed a lot of example of using to control a robotic arm or external device, but how do you see it instead more for rehabilitation? Actually, Marco and the speaker of tomorrow, Andrea Biasucci, they have a wonderful work in which they show that detecting the motor intention to then trigger either electrical stimulation, functional electrical stimulation for rehabilitation has a tremendous impact, and it seems to be a good way. What is your thought on that? Would you implant a stroke patient into the motor cortex to then, use this more for rehabilitation instead of for restoration?
Absolutely. And I think, so there's a couple of sides to that. One is, I think that there really is some opportunity to improve our outcomes from acute rehabilitation. For those people who are familiar with the North Star study that was done, which was really just cortical stimulation coupled with rehab, which unfortunately was not a very well designed clinical trial and really probably never had any hope of reaching a meaningful endpoint. So it did not show benefit. But certainly anecdotally, some of those patients who coupled their rehab with cortical stimulation in the acute rehab period seemed to actually do much better than expected. And again, those were small numbers. The other thing is that there is clearly some evidence that using some kind of directed rehab is beneficial. And so if you just have somebody go through the motions of using a exoskeleton or something without, or just doing sort of an intent thing, if you add those two together, clearly there is an added benefit. And so I think that is one of the areas that we really stand to be able to make a big difference. I think the biggest question becomes deciding how much or what's too invasive or what is invasive enough. And, you know, is this something where we design it to be a one-year implant, or is it something that we design that it could potentially be left long-term, knowing that maybe after that first year we have enough recovery that we don't need it anymore. But I think that, you know, that is an area where we have really looked at as being in that sort of an area to expand. On the cynical side, or maybe the practical side or the commercialization side, you know, the stroke rehab world is much, much bigger than the quadriplegic world. And so from the idea of commercialization, boy, that's the way to go.
Thank you.
And I have one more question from Marco. He's asking like how difficult would be in explanting an electrode. I believe the invasive electrode. So how difficult would it be for the patient as well as for you?
All right. So if we're talking about something like the Utah array, when you go back to surgery, certainly if it's at over a year, there is a fine layer of scar over top of it. But that scar can be incised, and then that sort of comes off pretty darn easily. And once you have gotten past that, lifting the electrode out, at least, you know, what we saw, and based on what we saw with electron microscopy of the electrodes, they're really not intercalated into the tissue. And this sort of goes along with some of the studies that have already been done by other people looking at that glial scar that forms at the interface between electrodes in the brain. So essentially, it makes it really easy to pop it out. If we look at the ones that go in the epidural space or in the subdural space, we have some animal data that we looked at. Again, a fairly significant scar was formed around it, although we still had good recordings. But removal was really easy. You just took a scalpel and you opened the scar up and then you just slid it right out. So at least for a lot of the devices we're currently using, there seems to be fairly easy to remove it. Now, Tracy Quee in Pittsburgh was very interested in coating electrodes with neurotrophic factors with the idea that we would then eliminate or reduce that glial scar that formed, with the hopes that we would get higher quality and longer, greater longevity in our signals. And that, so then I don't know if in those settings would we then engender more tissue damage at the time we removed the electrodes. So I think that leads a little bit to be determined. And then I think for some of these ideas of having sort of these biohybrid electrodes, where we actually use electrodes that are embedded in a substrate that is very conducive to neurons growing into them, now that really becomes a challenge, because you probably can't remove those, because that probably truly becomes intercalated into the brain. But as long as that's how you built it and designed it, and that's your expectation, then that's probably okay.
So, yeah, I think we are past out of time, but we have some interesting questions from the attendees. I think you can answer them. They are really interesting. Yeah.
Okay.
Thank you.
You're welcome.
Thank you very much for accepting our invitation.
Oh, it's wonderful. It's very nice meeting all these new people. Thank you.
Thank you, Elizabeth. Really, thanks again. It was an amazing talk and a lot of questions. Please, really, if you can answer, there are many student interest in knowing more. So it's fantastic, honestly. I mean, the perspective you give was great.